and today we'll be mainly talking about fingerprinting. So what is fingerprinting? Well, it's basically a game played among three people who are three cooperating people. Although, you could have more, but it doesn't matter. So let's start with a general case. We'll say we have A1, A2, A3 through A sub k. They have strings x1, x2, x3 through xk. And they want to send their strings to some, okay? Or rather, they don't want to send their strings. They want to send information to some responder. And the responder has to tell which should say which xi are equal. And the basic idea is that each Alice takes her string and gets a fingerprint. X3, and then sends f of xi to the responder, and responder compares f of these fingerprints. So first we're going to say, well, let's abstract this to a more rigorous game. And second, when can you do it and can you not do it in the classical situation? Because, because the quantum fingerprinting algorithm does better than the classical fingerprinting algorithm. But before we understand that, we have to understand when the classical fingerprinting algorithm works and when it doesn't. So first thing is actually, we can just worry about two Alices, and we will rename the second one Bob. So we have Alice and Bob. Each of them has a string, and they send some information to a responder who says, is x1 equal to x2? And to make this game more interesting, let's say there's some adversary who knows Alice's and Bob's strategy and gives them their strings. So this is we're looking at the worst case, or rather, the worst case strings for any given strategy. Yeah?
What's the goal? What are Alice and Bob's goal?
Alice, Bob, and responder are all working together to decide whether x1 equals x2, and Alice and Bob want to minimize communication. And if they had random strings, they could just send the first 20 bits of the random string and get a probability of winning 1 in a million, which is why we're making the string supplied by an adversary who knows Alice and Bob's algorithm.